Hello everyone, welcome back to the another session in design and analysis of algorithms. We'll be going to discuss about graph coloring using backtracking. This topic you'll find in 4th unit, topic number 3. Now let's get started. So what is graph coloring? This topic, graph coloring problem, this can be solved using backtracking. First of all, let us know what the problem is. Now consider this is a graph. I'm just marking the vertices, some 1, 2, 3, 4 vertices. And the problem is we have to color these vertices of the graph such that no two neighboring vertices or adjacent vertices must have same color. So these colors, what are you given with, that you have to fill in this vertices. Keep this in your mind that no two adjacent vertices have the same color. Now, so I'm giving two colors, red and green color. So first vertices, if I filled with the red color, now I just take red color. So now the neighboring vertices or adjacent vertices are what for 1? 2 is the adjacent and 4 is also adjacent. So according to the constraint of this graph coloring problem, you cannot fill the same color, which is red color, with this 2. You cannot fill. And here also red cannot be useful. What you have to use? You have to use green color. And here also you have to use green color. Now again check. Now one vertex is having red color and this is having green color. So different color. Okay. Here also different color. Again you should have what? Red color. You cannot place here green color. Did you understand? Now this is what graph coloring problem. Now let's see. Let G be a graph and M be a given positive integer. We want to discover whether the nodes of G can be colored in such a way that no two adjacent nodes have the same color, at only M colors are used. This is called as M colorability decision problem. This is called as M colorability. This is 2-mark question in the previous question papers of OU. M colorability decision problem. So the name itself, it tells that you have to take a decision based upon the graph what you given. You have to find it out. What are the colors? How many colors are possible, quite possible to color where two adjacent nodes will not have the same color. So this is called as M colorability decision problem. There is one more problem which is optimization problem. M colorability optimization problem. Now let's see what it is. Note that D is the degree of the given graph, then it can be colored with D plus 1 colors. The M colorability optimization problem asks for the smallest integer M for which the graph G can be colored. This integer is referred to as the chromatic number of the graph. So how many possible solutions we'll get? So once after you fill the colors in the graph such that you don't have any two colors same for adjacent vertices. Now I'll give an example to understand in better way. You consider this as one graph and graph with 5 vertices and you given with 3 colors, red, green, blue. You given with these 3 colors, right? Now let's assume I wanted to fill. It is not M colorability decision problem because you given with the colors. When you given with the colors, you need not to find out how many colors are required. Still you can have a M colorability decision problem. For this problem, even I can also use 4 colors. I can also use 5 colors, and 5 colors is the 6 colors is the at most. If you have M nodes, then M colorability decision problem will tell you M plus 1 colors or the maximum colors where you can use it. So the minimum colors also you should have, right? The minimum is what? You cannot use 2 colors for this 5 vertices. You have to use only 3 colors. It is of minimum. Now let's see. I am given with red, green, blue. Now let's see what is M colorability optimization problem. So I wanted to make this first vertex with red color. Okay. Now when I given with this red color, it very sure that my 5 vertex and second vertex should not have red, correct? So I cannot have red over here, I cannot have red over here, because as these two are adjacent to 1. Now I can also go for green or blue. So I am going for green for second vertex. Yes, I can go because it is red and it is green, two different colors. Now, which are the adjacent vertices for this two? One is 5, the other one is 3. 3 and 5 are adjacent to 2. So naturally, you cannot fill 5 vertex with the green. So green cannot be, correct? So anyhow red cannot be as one is having. So G also, green also cannot be for 5 vertices. Then what else you have the option? Blue color. Now mark it is blue. Now again come to this third vertex. G, green color is filled already here for second. Blue is already filled. Now you can take red color. No problem at all, because 1 is not adjacent to 3. So you don't have any problem. You are following the constraint still. Now again take the 4. 4 vertex is adjacent to 3 and 5. So can I take here red? No, I should not take red because third vertex is having red. Can I take here blue? No, already blue is for 5 vertex. I can have a chance of taking G. So what are the possibilities that I can fill the colors 1, 2, 3, 4, 5. These are the vertices. Now my first solution is what? First vertex can be filled with red, green, blue. Whatever we just had a discussion, that colors I have marked over here. Do I have any other chance of filling the different colors? Now still we can go ahead. That is, you can also go for one more solution, where that solution is what? And the second solution is, I can also go for, let's see, I wanted to take, I'll mark with different ink. I will be taking here green. Yes. So if I take here green, it is very natural that you should not take green. So shall I take red? Yes, I'll take red. So when I take here red, for 5 vertex, you should not take red and green. So natural it is, you have to take blue. Now again come back. So in second vertex is adjacent, and here you have to take green. So here you have to take red. So you can have multiple solutions, right? It is not optimization thing that you have to have maximum number and minimum number, but we are checking all the possible solutions what I can get for this. Now permutations which are neighboring the vertices should not have same color. So if you given with 2 colors, you cannot find solution. That's what M coloring decision problem will tell you. How many colors are required, minimum number of colors which are required to color a graph. That problem is called as M coloring decision problem. M coloring optimization problem is what? How many possible cases will be having? So that is what M coloring decision problem. Now let's take some example. So this is book example I am taking, exercise. So you can see the prescribed textbook. There are abundance of examples to be done by you guys. You can take any of the example. So I'll write even program for the same example. So you can take other example to implement your code, because this is also one of the example part of your lab series. Now I'm taking the example as 4 vertices graph. 1, 2, 3, 4 vertices graph and 3 colors. Now let's see how I can fill these colors, or what all possibilities without checking any condition. Then we will be come to know how much we were reducing with the backtracking. Now there is no constraint, just I am going with the filling the colors, and I am seeing what are the possibility of the state space tree. Now first of all, I wanted to take the 3 colors, and as I have 4 vertices now, so I am taking first vertex possibility. I am taking x1 is equal to r. My first vertex is filled with red color. So when it is given with red color, natural that 2 should not have red, 4 should not have red. You can take the other color. Okay. Now, so I told you this state space tree is, I am not using any constraint, any condition. I am just simply calculating the number of nodes. How can I generate for these colors? So x2 also I am making with red color. Okay. Now x3 also I am making with red color. Now x4 also I am making with red color. Now, so now the constraint is what? You cannot have red color. So go back. x3. Do you have any other possibility? Yes, I have a possibility. What is that possibility I have? That I can go to take the other color, which is green or blue. And here also, if it is red color, it is green and blue. The same, if it is red color, it is green and blue. If it is already green and already red is done, and it can be of blue. It can be of R, G, and again of B. Right. Now let's see. This is what your state space tree, and here you will be having what are the colors you are going to choose for the vertices. Now, possibly, how many colors you will get for this? That how many nodes you will be get for this? That total number of nodes without bounding function, without any condition, you will get. Under this root node 1, you have how many nodes? 3. 1 into 3. First level. In the second level, I have 3 nodes. That is of 3 into 3. Plus, in the next level, 3 nodes and multiply with 3. That means 27. 3 into 3 into 3. In the next level, 3 into 3 into 3 into 3. Now, calculate this one. 1 plus 3 power 1 plus 3 square plus 3 cube plus 3 power 4 is equal to 3 power 4 plus 1 minus 1 by 3 minus 1. That is 3 power 4 plus 1 minus 1 by 2. And which is 3 power n plus 1. Now this 3 is for what? This number, right? I have taken 3 colors, so I have got 3. If it is for other number, chromatic number, I am indicating with C, and it is n plus 1, C power n plus 1. The time complexity which is required for generating the number of nodes to fill the 3 colors is exponential time, C power n plus 1. Now let us solve using the same problem. Let us solve the problem using the backtracking. That means applying the bounding function. If once you apply the bounding function, your bounding function is what? When the possibility is not there, when you are not satisfying the constraint, we'll just kill the node and no more extraction from this. So you will reduce definitely time complexity, right? Now let's see that. So I'm taking the other state space tree, and here I'm using bounding function. Now I'll take the graph 1, 2, 3, 4. So I'm given with again the same example. I'm taking 3 colors. Those 3 colors are RGB, red, green, blue. Now, so the first case, I'm filling the first vertex with red color. So it is red color. Now when it is red color, x2 should not be red because it is adjacent vertex, correct? So I cannot take x2 red color. If I take x2 red color, I have to kill this node. There is no extraction further. So I'll stop here itself. Now, so do I have any other possibility? Yes, you can choose the other different color. Now I'm choosing green color. Now it is green color. So can I move? Yes. So I told you in the beginning of backtracking video, it is DFS. Now x3 is equal to red color. Can I make it is red? Yes, because 2 is adjacent to 3. 2 is having green color, so you can make it is red color. So now x3 red. So now I can go for x4. x4, if I keep it is red color. Now it is red color. What happens? Now there should not be red color, right? Now 2 adjacent should not have the same color. So you have to kill this node. No extraction. You are killing this node. So come backtrack. Now what happens? As x3 is already red, as x1 is already red, you should choose either green or blue. So there will be 2 possible solutions. One is with green, the other one is with blue. These 2 are possible solutions for this. Now again go back. x3 is equal red we were taken. Now let us see if x3 is green. Now what happens? Now it is again similar, same color. So kill the node. Apply bounding function and kill the node. So again take B. That is what? Blue color. So when it is blue color, again three possibilities, that if it is a red color, then again kill the node. If it is green color, yes, it can be. If it is a blue, again kill the node. So the reason I'm killing the node is what? I wanted to cut the extraction of the next level, because as per the condition satisfaction that no two adjacent vertices have the same color. So depending upon this, I can get the possible number of solutions for this is first vertex can be filled with red, and the second is with green, and the third with green, and the fourth is with green. So we'll take again the graph back. I feel it is something clumsy. So I'm just taking the graph again. Now look at this. So what possibilities I can have? The first possibility is red, green, red, green. Yes, fill it. Red, green, red, green. No, there is no problem to fill these colors. Yes, it is okay. It is one of the solution. Now, what is the second solution? Your second solution is red, green, red, blue. Still it is accepted. Now, let's see. First vertex is red. Second vertex is green. And it is red. It is blue. Still it is okay. Now, the third case. Red, green, blue, green. It is also fourth. Red, blue, red, green. The fifth possibility, red, blue, red, blue. Now, so when you take these things, these are the solutions of this graph, right? Now, you have a question, where the graph coloring is useful? Why graph coloring? What is this colors to fill in the vertices? Now, I'll come up with a good example for you all. Now, let's see, it is a Telangana state map. So, you can find out some colors over here. Now, if I wanted to fill different colors for each district of Telangana, I repeat my statement once again. If I wanted to fill different colors for this district of Telangana state, then if Telangana is having n districts, you need n different colors to map. So it is a cost process, right? You should take each color to get print, or you should choose each different color every time. So what we are doing is we are giving a solution with the graph coloring. So what graph coloring suggests is you can take limited number of colors, keeping in mind that no two adjacent colors will have the same. No two adjacent vertices will have the same color. So this is what a beautiful solution for these kind of problems. Now there are very similar colors. Here it is green and green. Here also it is green. And it is orange. You can find same. This is also orange. You can find same colors over here. But using n different colors is very different from using m coloring decisions. When you given with n vertices, let us suppose I have vertices of 33. Then I can take maximum of 34 colors where it is little bit costly, right? But we can take limited number of colors. So that is what m coloring decision problem. Now we'll take some algorithm to understand this m coloring problem. So in m coloring problem, so that is what this algorithm was formed using the recursive backtracking. The graph is represented by its Boolean adjacency matrix G1 to n to 1 to n. All assignments of 1, 2 to m. So far we were taken red, green, blue, right? Now onwards we are just indicating these colors with the numbers 1, 2 up to m to the vertices of the graph, such that adjacent vertices are assigned with distinct integers or printed. K is the index of the next vertex to color. Now we'll be going to generate all legal assignments for x of k. Now the next value is k. That means we are assigning x of a a legal color, next value legal color to array. Now if x of k double equal to 0, then we are written that no new color is possible. If x equal to n, then at most m colors have been used to color the n vertices. So now that we'll write into the array, and we will be going for m coloring to see for which vertex which color has to be, right? We will be recursively call this function. So this is about graph coloring, and where you will use, why you will use, what is m coloring, decision problem, optimization problem through a state space tree. Thank you all.